Hi friends, welcome to our YouTube channel Knowledge Academy. The main aim of this lecture is to discuss about the communication systems of IES or ESE Previous Year Prelims questions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever we upload a new video, the direct notifications comes on mobile. If any improvements in our video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to solve the 151 question. See the question here. Differential pulse code modulation is particularly used for. So for what type of signal transmission we are going to use the differential pulse code modulation? So out of these four options, option C, speech signals transmission is the correct solution of this question. So let's solve this question. So basically here the Dpcm is nothing but differential pulse code modulation. This is the transmitter circuit of a Dpcm. So basically this Dpcm and the PCM are going to convert the analog signal into a digital signal. So basically here we are going to use a sampler. Sampler is going to sample each and every signal, or we can say at each and every amount of time we are going to sample the M of the signal, analog signal. And then here we are going to use the quantizer in order to make a fixed number of levels. So basically in the PCM there is no feedback, but here in the Dpcm we are going to give a feedback so that whatever the output you are going to get, it is a difference of the current sample minus previous sample. So the error is going to get decreased, and then we are going to encode here, and then we are going to convert into a digital format. So basically here in the PCM, here in this Dpcm we are going to use the fixed number of levels. So fixed number of levels are going to use in the quantizer in the Dpcm. So because of this circuit here, we are going to decrease the amount of the bandwidth required in order to transmit this digital signal, and also the number of bits at the digital format is also going to decrease, and also signal to noise ratio is also going to decrease with the help of Dpcm when compared to PCM. And because of these things, it is going to basically use for the speech signal transmission and also the video. So video, speech and images, all these can be transmitted with the help of the Dpcm circuit. And also there are two problems are going to occur in this Dpcm, which are the slope overload distortion problem and also the quantization noise. These two problems are going to present in this Dpcm. So quantization noise is nothing but it is a small amount of error between the actual value and the quantized value. So that's called as a quantization noise. And if you are going to compare the PCM and the Dpcm, here the number of bits in the Dpcm is very higher when compared to the number of bits present in the PCM, except this remaining everything is going to become less. So therefore the complexity of the circuit in deciding the Dpcm is lesser when compared to the complexity of circuit in order to decide the PCM. And also the frequency sampling. The frequency sampling we are going to use for the sampler in Dpcm is less when compared to the frequency sampling which is used in the PCM. And also it is a efficiency. So efficiency of Dpcm is very higher when compared to efficiency of the PCM. And also the number of bits in the Dpcm is lesser than the number of bits used in the PCM. And also the bit rate of Dpcm is very less when compared to bit rate of the PCM. And we can say the bandwidth in the Dpcm is also less when compared to bandwidth of the PCM, and the signal to noise ratio in the Dpcm is always lesser than the signal to noise ratio in the PCM. So because of the using the feedback, we are going to get everything in a low manner, means the efficiency is improved in Dpcm when compared to efficiency of PCM. See, if you want to make a circuit of PCM, it is very complex, but making this Dpcm is very less complex when compared to PCM. So we can say these are the way of comparing the Dpcm and also PCM. So we can say finally this Dpcm is going to get a signal which is the difference of the actual current sample minus the previous sample. So regarding that difference only we are going to get the output. So therefore it is basically used for the speech signal or images, or we can even say the video signals. These signals can be transmitted with the help of these Dpcm circuits. So now we are going to solve the 152 question. See the question here. A comparison of FDM and the TDM systems shows that, so FDM is frequency division multiplexing and TDM is time division multiplexing. So basically we are going to compare these two things. So out of these four options, option B is the correct solution of this question, which is FDM has a greater noise similarity and requires lower bandwidth than the TDM. So now we'll discuss the solution. So now we'll discuss some of the important facts regarding the multiplexing. So here, suppose a data is coming from different sources. So if data is coming from different sources, I want to send this data in a common channel. Then the method we are going to prefer is called as a multiplexing. So with the help of this multiplexing, we can make all this data to come into one single channel, and then we can give it to a receivers. So basically multiplexing is of three types. The first one is the TDM, time division multiplexing, and the second one is the FDM, frequency division multiplexing, and the third one is the WDM, wavelength division multiplexing. So we are going to compare only the TDM and the FDM. So TDM is time division multiplexing and FDM is frequency division multiplexing. So basically here we are going to send the signals based on the time slots, means we are going to divide the time into different time slots, and we are going to give this time slots for each and every input signal. And then here we are going to always use the synchronization per signal so that we can differentiate the message signals. So therefore now it is also used for the digital and as well as the analog signals, and this amount of multiplexing in order to send the signals based on it is the examples which are using this TDM are the telephone companies, and also internet service providers are going to use this TDM technique in order to send their signals. And the circuit in order to make this one is very less complex when compared to FDM. Whereas the FDM here we are going to send the input signals based on a frequency domain. So therefore we are going to give the signals based on a frequency domain, and also here there is a guard band between the frequency message signals. So therefore there is no overlap between the signals. Suppose in the frequency domain this is the message signal 1 and the message signal 2. So this is called as a guard band. So guard band is going to give you so that it can protect from overlapping between the two signals. And here we have to the circuit design is very complex when compared to the TDM. And also this frequency division multiplexing is used in the radio and also TV. So the cable TV operator is also going to use this FDM way in order to send their signals. So therefore we can say radio and the TV are the best examples. They are going to use this FDM technique. So therefore we can say here the bandwidth of the TDM is sampling rate by 2, which is NFS by 2, and the bandwidth in the FDM, suppose if you are going to use the dual side bands, the number of signals into 2 times the bandwidth of each message signal plus n-1 into guard band. This is the overall bandwidth. So from this we can see that the bandwidth of the FDM is very less when compared to bandwidth of the TDM, because here in the TDM we are going to use each and every signal, or we can say each and every time domain is fully used, but where in the FDM some amount of is not used because we are going to keep a guard band. So therefore now here full frequency domain is not used because we have to give a small guard band, so therefore there is no overlapping problem is going to present. So because of that we are full bandwidth, full range of time domain or bandwidth is used only in the TDM when compared to FDM. So because of this reason only we can say the bandwidth of FDM is very less when compared to bandwidth of TDM, because here we are going to use some amount of extra guard band, so therefore that range is not utilized anywhere. So because of that we can say bandwidth of FDM is very less when compared to bandwidth of the TDM. And also the noise immunity of FDM is very high when compared to the noise immunity of TDM, because there is a synchronization pulse is required for the TDM, whereas here guard band is there. So therefore because of guard band it can say that there is no overlapping present between the two signals, but here there is a synchronization pulse is required for TDM. So because of this we can say the noise immunity of FDM is very high when compared to noise immunity of the TDM. So now we are going to solve the 153 question. See the question here. In time division multiplexing, crosstalk may be avoided by. So in the TDM we can eliminate the crosstalk, because of which reason? So out of these 4 options, option B is the correct solution of this question, which is the proper selection of time of sampling. So because of this we can remove the crosstalk. So now we'll discuss the solution. So now we'll discuss some of the important things regarding the TDM. TDM is called as a time division multiplexing. Suppose here there are 4 inputs. So these inputs are going to give you messages. So by using this time division multiplexing, here there is a mux. So mux is going to convert. See here we are going to divide this channel into time slots. So we are going to fix the time slots for each and every message signal. So for the first time slot we are going to send the message signal A, and for the second time slot we are going to send the message signal of B, and for the third time slot we are going to send the message signal C, and then for the fourth time slot we are going to send the message signal D, and then it is going to A, B, C, D. So it is going to repeat in a sequence manner. So therefore here by using the demarks we can convert back the again output streams like A, B, C, D. So we are going to use the time domain here, means we are going to divide the time into fixed slots, and we are going to use that slots for the each and every message signal in a round conference. We can say it in a round sequence. So because of this here we are going to use the full bandwidth of the TDM, or you can say full frequency time domain also we are going to use for the TDM. Suppose if you are not going to use the proper synchronization between the input or between the receiver and also the transmitter, so we can say we have to use the proper synchronization between the transmitter and the receiver, otherwise there is a crosstalk, means one message signal can overlap with the other message signal, means here there is a possibility of overlapping between the two message signals if you are not giving a proper sequence of synchronization, or we can say if you are not giving a proper way of sampling, or suppose if you are not giving a proper time of selection of sampling, or we can say proper synchronization, then the message signals can overlap in the time domain. So that is the reason always it is necessary to give a time of sampling between the two independent things. So by properly selecting the time of sampling, or we can say the proper sequence by using the proper synchronization between the transmitter and the receiver for each and every round of way of C after ABCD again ABCD. So with the help of proper synchronization or proper time of sampling, we can avoid the crosstalk between the message signals which are received at the receiver. So now we are going to solve the 154th question. See the question here. Consider the following statements comparing delta modulation with the pulse code modulation system. So we are going to compare the delta modulation and the pulse code modulation. So out of this, which of the above statements are correct? So out of these four options, option B, 2 and 4 is the correct solution of this question. So let's solve this numerical. So now we'll discuss the important difference between the delta modulation and the pulse code modulation. So this is a circuit transmit diagram of a pulse code modulation. So there is an analog signal I want to convert into digital format. So then I am going to use a sampler here. So because of sampler, with the help of sampling frequency, we are going to convert this analog signal into a sample of signals. And then with the help of quantizer, I want only fixed number of levels but not arbitrary. So I am going to convert all these arbitrary into a fixed number of signals. So because of this quantizer only, there is a quantization error. And also here there is an encoding, means with the help of these fixed levels we are going to now convert into a digital signals. Here more than one digital signal we can send, means more than one bits are going to send with the help of PCM. Now whereas the delta modulation, here this is the transmit diagram of a delta modulation. Here we are going to use a analog signal, like we are going to convert into digital signal of only one bit. So here we are going to use a comparator, and also we are going to use a feedback in such a way with the help of delay and the staircase. Here we are going to get an output only which is called as a only single bit. We can only get a single bit in the delta modulation. So now we are going to compare these two circuits now. So here in the sampling rate of delta modulation is very higher when compared to sampling rate in the pulse code modulation, and also the bandwidth in the PCM is very high when compared to bandwidth. Suppose if you want to transmit a digital data of more number of bits, because more number of bits are present in PCM, so because of that reason we can say the bandwidth required in order to send digital data in PCM is very high when compared to a bandwidth in the DM. And also the complex of circuit, so we can say the complex of circuit in the digital delta modulation is very less when compared to PCM, means the amount of complexity of the hardware in the delta modulation is very less when compared to the complexity of the hardware in the PCM. And also the PCM is very costly method when compared to the delta modulation, and also the signal to noise ratio in the delta modulation is very less when compared to signal to noise ratio in the PCM. And this PCM is going to basically use for those analog signals of the audio and the video, whereas the delta modulation is going to use for those analog signals of the images. So these are some of the important difference between a delta modulation and also PCM. So therefore we can say the bandwidth in the PCM is very high when compared to the bandwidth required for the delta modulation, and the complexity of the hardware in delta modulation is very less when compared to the complexity of the hardware in the pulse code modulation. And also the sampling rate in the delta modulation, means the amount of sampling frequency required in order to sample the message signal in the delta modulation is very high when compared to sampling rate in the PCM. So these are some of the important difference between a pulse code modulation and also delta modulation. So now we are going to solve the 155 question. See the question here. Statement 1. The PALM, PWN and the PPM modulation belongs to analog modulation and the PCM modulation belongs to the digital modulation. So and the statement 2. PALM, PWM and the PPM modulation are similar to AM, FM and PM modulation. So basically here both the statements are correct. Individually they are correct, but the statement 2 is not the correct explanation of the statement 1. So option B is the correct solution of this question. So let's discuss this question. So basically the PALM, pulse amplitude modulation and the pulse width modulation and the pulse position modulation, these three are going to belong to the analog modulation schemes. And also here PCM, pulse code modulation, belongs to a digital modulation. So we can say here the PALM is nothing but pulse amplitude modulation. So PWM means pulse width modulation. Pulse width modulation is also called as the pulse duration modulation or the pulse time modulation, and the PPM is the pulse position modulation. So basically here in the pulse amplitude modulation we are going to change only the amplitude. We are going to change only the amplitude of the output, or we can say the carrier signal only amplitude part we are going to change but not the width. So it is similar to AM. In AM also we are going to change only the amplitude but not the frequency, or width is nothing but the frequency. So only amplitude part is we are going to change in the PALM. So it is similar to AM modulation. In the PWM we are going to change only the width of the signal, carrier signal only we are going to change only the width of the signal but not the amplitude. So amplitude is a constant, only width we are going to change. If we are going to change the width, it is nothing but a frequency. So therefore it is called as a frequency modulation. Whereas the pulse position modulation, here we are going to change only the position of the signal with respect to the message signal. With respect to the instantaneous values of the message signal, we are going to change the position. So therefore, but the amplitude and the width are remains constant, but only thing is position. So it is nearly equal to phase modulation. In the phase modulation also we are going to change only the phase part. So it is nearly equal to PPM. So PPM is nearly equal to phase modulation. But here in all these three modulation signals we are going to use a discrete, or we can say some discrete form of the carrier signal. Means it is not a continuous format. But in the analog modulation, FM modulation and PM modulation we are going to use a continuous carrier wave signal. So listen carefully. In all the PM, PWN and PPM we are going to use a discrete, or we can say discontinuous, carrier signal we are going to use. But here in the AM, FM and PM we are going to use a continuous carrier signal we are going to use. But in the PALM, PWM, PPM we are going to use the discontinuous carrier signal we are going to use. And in the AM, FM and the PM we are going to use the continuous carrier signal. This is the only difference between these two things, and the remaining everything is same. So therefore here in PALM we are going to change only the amplitude part we are going to change, and in the PWM we are going to change only the width part, but the amplitude part is constant. But in the PPM we are going to change only the position with respect to the instantaneous message signal, but the amplitude and the width are going to remain constant of each and every pulse. So this is all about the difference. So we can say this statement 1 is correct and the statement 2 is also correct, but statement 2 and statement 1 are independent of each other. So this is not a correct solution of the statement 1. So now we are going to solve the 156th question. See the question here. If the probability of a message is 1/4, then the information in bits is. So if the probability of a message signal, or you can say it is 1/4, then what is the information in bits? So out of these four options, option B, 2 bits is the correct solution of this question. So let's solve this numerical. Here, before I solve this numerical, let me tell a small concept here. See here where MK is called as a message signal which is transmitted with the probability PK. So here MK returns the message signal which is transmitted with the probability of PK, and IK is called as the amount of information received at receiver in the terms of bits. So it is going to tell you about the amount of information which is received at the receiver in terms of bits. The relation between these two things is IK is equal to log to 1/PK. So here PK is the probability of the message signal and IK is the amount of information received at receiver in terms of bits. The unit is bits. Suppose if you want to convert in terms of the base 10, the formula is 3.32 into log 10 1/PK. So in this question they are given the amount of the probability of the message signal is 1/4. So we have to find what is the information in terms of bits. So I am going to use this first formula, which is I is equal to log to 1/PK. So therefore I is equal to log to 1/P. P is 1/4. So 1/1/4 is nothing but 4. So log 4 base 2 is nothing but 2. So 2 bits are required in order to transmit, or we can say the number of bits required is 2 bits for this probability of message signal for 1/4. So now we are going to solve the 157th question. See the question here. A conventional telephone line with 3 kHz bandwidth and having 30 dB signal to noise ratio can carry information at a rate. So in this question they are given a bandwidth of 3 kHz and also the signal to noise ratio in dB is 30, and then we have to find what is the information carried at a rate. So what is the information carried at a rate we need to figure out. So out of these 4 options, option A is the correct solution of this question, which is the 30 kilobits per second. So let's solve this numerical. So in this question they are given a telephone line company has a bandwidth of 3 kHz and also signal to noise ratio in dB is 30. So based on this we have to find what is the information rate. It indicates that how many number of bits per second are being transmitted with the help of this channel we need to figure out. So here this is in terms of dB. I want to convert into actual value, which is 10 log base 10 s by n is equal to 30. So if you do the simplification, we are going to get the actual value of signal to noise ratio is 10 to the power of 3. So with the help of Shannon-Hartley law, we are going to give a relation between the channel capacity, bandwidth and the signal to noise ratio, which is channel capacity is equal to bandwidth into log base to 1 plus s by n. So therefore now if you want to convert this into log base 10, here the another formula is 3.32 into bandwidth into log 1 plus s by n with a base of 10. So basically here the C is called as the channel capacity and its unit is the number of bits transferred in a second. How many number of bits transferred in a second is called as a channel capacity, or we can say information rate. How much bits per second are being transmitted with the help of this one. So here we know the value of bandwidth and we also know the value of signal to noise ratio, the actual value. So we are going to substitute in this equation and we are going to get the value of C. So C is equal to 3.32 into B is nothing but here 3 kilohertz. So 3 into 10 to the power of 3 log base 10 1 plus s by n. So s by n is equal to 10 to the power of 3. So 1 plus 10 to the power of 3 is nearly equal to, see 10 to the power of 3 is very higher when compared to 1. So if you are going to add a small amount of 1, it is nearly equal to 10 to the power of 3. So log 10 to the power 3 by 10. So this is nothing but the value of 3 and the remaining is same. So the unit is bits per second. So if you do the multiplication, we are going to get 29.98 into 10 to the power of 3 bits per second, or we can say simply 30 kilobits per second are being transmitted with the help of this channel. So in a 1 second 30 kilobits are being transferred. So the channel capacity is 30 kilobits per second is a correct solution, and the formula is C is equal to the channel capacity is equal to bandwidth into log of 1 plus s by n with a base of 2, or we can say 3.32 into bandwidth into log of 1 plus s by n with a base of 10. So now we are going to solve the 158th question. See the question here. The channel capacity of a noiseless channel is equal to. So what is the channel capacity of a noiseless channel is equal to? So out of these 4 options, option A, rate at which the information is transmitted is the correct solution of this question. So let's solve this question. So for noise free channel, so basic condition is, suppose always the rate at which the information is transferred is always less than or equal to channel capacity. But for noiseless transmission, what is going to happen is there is no noise in the channel, so we can say we can use the maximum amount of channel capacity. So therefore the channel capacity, the maximum value is equal to the maximum rate at which the bit is transferred. So therefore the channel capacity is defined as the rate at which the information is transferred is equal to the channel capacity for a noiseless transmission. Otherwise we can go for the even lesser than that value. So therefore the RB can be lesser than or equal to C, but the maximum value can only be up to a channel capacity. And another formula of the rate is nothing but the bit rate is equal to R into H, where RB is called as a bit rate, or we can even say it is a bit information or the information rate. The unit is bits per second. So in a 1 second how many bits are being transferred, it is called as a bit rate or simply the information rate. And here C is called as a channel capacity. So C is called as a channel capacity, and it's also unit is also called as a bits per second, because they both are equal means both should have the same number of units. So we can use the maximum channel capacity for the noiseless free transmission. Suppose if there is a noise, we can use only a small amount of channel capacity, and R is called as the number of symbols or messages transmitted per second by the transmitter. So we can say R is called as the number of symbols or messages transmitted per second by a transmitter is called as the R. So its unit is symbols or messages per second, and where H is called as the entropy, and its unit is bits per symbol or messages, means for one symbol of messages how many bits we are going to use. And if you multiply these two things, the messages or symbols are going to get cancels and we are going to get the unit as bits per second. So therefore bits per second is called as a bit rate. So this is the actual formula of a bit rate, which is R into H. So where H is called as the entropy and R is called as the number of symbols which are transmitted in a second. So here if there is a no channel noise, we can say if there is no noise on a channel, then definitely we can use the maximum amount of bit rate we can use for the channel capacity. Finally, we can say for noise-free channel, we can say the rate at which the information of the bit is transferred is called as a channel capacity. So now we are going to solve the 159th question. See the question here. Which one of the following is the correct statement? If the channel bandwidth become doubles, then what is the signal to noise ratio becomes? See, if the channel bandwidth is increased by 2 times, then what is the nature of the signal to noise ratio? So out of these 4 options, option C is the correct solution of this question, which is the half of the previous one, or we can say it becomes half of the former signal to noise ratio. So option C is the correct solution of this question. So let's solve this numerical. So in this question, they are given a suppose if the bandwidth is increased by 2 times, then what is the nature of the signal to noise ratio we need to figure out. So basically, signal to noise ratio symbol is S by N, where S is called as a signal power and N is called as a noise power. So we can even write it as a symbol Pn or capital N. So Pn is equal to K into T into B, with K is called as a Boltzmann constant and T is called as the temperature in degree centigrade and B is called as the bandwidth of the signal. So here, suppose here the signal power is going to depend only upon the magnitude of the message signal. Means we can say the RMS value square of the message signal only it is going to depend. See, the signal power is called RMS of the voltage whole square. Only it is going to depend upon the RMS value of the voltage, but we can say it is independent of bandwidth. So independent of bandwidth, it is only going to depend upon the RMS value of the current signal or the voltage signal. So only it is going to depend upon the RMS value of the voltage or current signal, but we can say it is independent of the channel bandwidth. Only noise power is going to depend upon the bandwidth. So now suppose I am going to divide the S1 by N1 by S2 by N2. So therefore here I can write in another fashion, which is S1 by N1 into N2 by S2. See, as S1 and S2 signal powers are going to depend upon only on the signals, but it is independent of the channel bandwidth. In this question they have not given about the 2 different signals, so we are going to assume the signals are same, but only thing the variable is the bandwidth. So S1 is equal to S2, so we can say N2 by N1. So N2 is equal to K2 B2 by KT B1. KT is a constant, so therefore KT cancels, so B2 by B1. So we are going to increase the bandwidth by twice that, so therefore 2 into B1 by B1. So B1 cancels, we are going to get 2. So after simplification we are going to get, after rearranging we are going to get S2 by N2 is equal to 1 by 2 S1 by N1. So we can conclude that the signal to noise ratio is going to become half of the previous one. So if you are going to increase the bandwidth by 2 times, then the new signal to noise ratio will become the half of the previous one, or we can say half of the former, because signal power is going to depend only on the RMS value of the current or voltage, and it is independent of the channel bandwidth. So because of that category we are going to assume the signal is same, but only thing is we are going to change the bandwidth. So based on the bandwidth we have found the signal to noise ratio is half of the signal to noise ratio of the previous one. So now we are going to solve the last question of this lecture. See the question here. A communication channel is to receive signal power S and the noise at the receiver input is I2 thermal noise. With uniform power spectral density, it is found that if the bandwidth is 1 MHz, the channel capacity is 10 Mbps. What would be the channel capacity for the same signal power and the same noise power spectral density if the bandwidth is unlimited, tends to infinity? So here in this question they are given the same signal power and the same noise spectral density, means S by eta is same in the both cases, and also for the first case the bandwidth is 1 MHz and the channel capacity is 10 Mbps. Suppose for the second case, if the bandwidth is infinity, then what is the channel capacity we need to figure out. So out of these 4 options, option D, 1.5 gigabits per second is the correct solution of this question. So let's solve this numerical. So in this question they are given if the bandwidth is 1 MHz and the channel capacity is 10 megabits per second, and in the question they are given the signal power to noise power spectral density is constant for both the cases, and when the bandwidth is infinity, then we have to find what is the channel capacity we need to figure out for the same signal to power spectral density, so at the receivers. So here first thing is here noise power, we can write the noise power is equal to, or we can say N is equal to Pn is equal to KT into P, where KT is called as a power spectral density, which is eta into B is called as a bandwidth. So the formula by Shannon-Hartley formula, which is going to given by C is equal to B into log 1 plus S by N with a base 2. So In this question, in the first case, they are given the channel capacity is 10 megabits per second. So 10 into 10 to the power of 6 is equal to bandwidth is 1 megahertz. So 1 into 10 to the power of 6 log 1 plus s by n with the base 2. So 10 to the power of 6 and 10 to the power of 6 get cancels. So finally we are going to get 10 is equal to log 1 plus s by n with the base 2. So if we take here, finally we are going to get 2. If it goes here, 2 to the power of 10 is 1024 and 1 plus s by n is equal to 1024. So if I take the 1 here, finally we are going to get s by n is equal to 1023. So 1023 I am going to assume it is approximately equal to 1000. So therefore s by capital N is nearly equal to 1000. But I have already told you n is called as a noise power, which is Pn is equal to kT into beta. So kT is called as a eta, power spectral density. So eta into b, bandwidth is nearly equal to 1000. So I am going to take the bandwidth here this side. So signal power by noise power spectral density is nearly equal to 1000 into b, where b is called as a bandwidth. So bandwidth, how first case the bandwidth is 1 megahertz. So 1 into 10 to the power of 6. So 1000 into 10 to the power of 6 is nothing but 10 to the power of 9. So therefore we can say the ratio of the signal power by the power spectral density is 10 by 9. It is same for the first case and also for the second case. So now suppose if the bandwidth is infinite or unlimited, then what is the channel capacity we need to figure out. And the s by n is same for the first case and also second case, means the signal power at the receiver is same for first one and the second one, and also they are given the power spectral density is same for first and second case. So now we have to find what is the channel capacity we need to figure out based on the bandwidth and the s by n. So channel capacity is equal to bandwidth into log 1 plus s by n with the base 2. But here capital N is nothing but the noise power is equal to kT into beta, where kT is called as a power spectral density eta into b. So therefore I am going to substitute here. So here I am going to multiply s by theta into eta by s. So same thing we are going to get, because they both are going to cancel and we are going to get the same as the previous one. So log 1 plus I am going to replace capital N by eta into b with a base 2. So now here I am going to multiply this b inside. So finally I am going to get s by eta into b eta by s into log, same thing as the previous one. So log of 1 plus s by eta b into base 2. So now I am going to take this one to the upper part. So finally I am going to get s by eta into log 1 plus s by eta b 2 with the whole power of b eta by s. So now I can write in another fashion, which is 1 by s by eta b, and same as the previous one. Everything is same, just I made this one 1 by s by eta b. So now I can assume here x is equal to s by eta b. I can assume this value as x. See, whenever the bandwidth is infinity, so whenever the denominator is infinity, the overall value will become 0. So whenever the beta value tends to infinity, x value tends to 0. So already we have known in mathematics, whenever the limit x tends to 0, 1 plus x whole to the power of 1 by x. So this is x. So now this will become 1 by x. So limit x tends to 0, 1 plus x whole to the power of 1 by x is nothing but it is nearly equal to e. So therefore this all value will now converge to e. So therefore s by eta into log e base 2, because all this value is now converged to e, because whenever the bandwidth is infinity, all this value will converge to e based on the mathematical relation. So therefore we can say s by eta into log e base 2. So s by eta already we have known, which is the ratio of the signal power to the power spectral density. It is constant for the first case and also second case. Its value is 10 to the power of 9. So and log e base 2 value is 1.44. So this many number of bits per second has been transmitted. So therefore we can say 1.44. So 1.44 gigabits per second has been transferred. It is nearly equal to 1.5. So therefore this many number of gigabits per second has been transmitted. So therefore, so the channel capacity is 1.5 gigabits per second. See, 1 mega is nothing but 10 to the power of 6, 1 giga is nothing but 10 to the power of 9, and 1 nano means 10 to the power of minus 9. So therefore here 10 to the power of 9 means giga. So therefore we can say 1.5 gigabits per second, nearly this way number of bits are being transferred whenever the bandwidth is infinity. In this question they are given signal power to the noise power spectral density is constant, means noise power spectral density means eta value is constant. So by this lecture we have successfully completed the 160 questions of communication systems of IES or ESE in a prelims questions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever we upload a new video the direct notification comes for a while. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep small and take care, and bye bye.